Good morning, all. Myself, I am Sharath from Energy Management Center. Hope I am audible to everyone. On behalf of Energy Management Institute of the Energy Management Center, Kerala, a warm welcome to the program. EMC Energy Management Center under Department of Power, Government of Kerala is the state designated agency of Bureau of Energy Efficiency, India. It's a Bureau of Energy Efficiency comes under Government of India, Ministry of Power. And these two organizations are established under the Energy Conservation Act 2001. The new technological trends in energy efficiency and sustainable development are being introduced in the industries through which drastic reduction in their energy consumption profile are attained. EMC was organizing various kinds of awareness training programs focusing on energy management, energy conservation in various sectors throughout the year, and we were organizing it in each and every place in Kerala. But I think I am audible to everyone. I saw a comment. Okay, thank you. So we were conducting training programs in various sectors on energy management and energy efficiency. But due to the present scenario of COVID-19 and the subsequent lockdown and the restrictions, it was not able to conduct the training programs in the conventional manner. That is, we cannot organize training programs like what we did in the earlier period. So we moved to a digital platform for conducting these training programs. That is, we organize webinars on various subjects. During this year, EMC is organizing a series of webinars on various topics. The first of its kind was started on June 1st of this year, World Environment Day, and this will be lasting to the next year. And we have given a title for this webinar series also as Energy Efficiency in All Walks of Life, from Lamps to Boilers. And we have published a webinar calendar, which is published in the EMC website also. So, Government of India has notified Energy Conservation Act, which came into existence from March 2002, and it got implemented from 2006 in a full-fledged manner. And with the powers of Energy Conservation Act, Government of Kerala has already made energy audit mandatory to all high tension and extra high tension consumers in the state, and they should perform energy audit once in 3 years and submit the energy audit report to EMC. The energy audit report submitted to EMC will be evaluated by an expert committee, and the suggestions will be given to the consumers as well as the energy auditor. And this has been followed from 2011 onwards, and this was done for enhancing the quality of the energy audits happening in the states and also increasing the intensity of the energy audits happening. For that, EMC has empaneled 45 energy audit firms from all over India for performing the energy audit. So, as we all know, energy audit is the evaluation of energy efficiency in the already installed appliances. So energy audit is basically the verification, monitoring, and analysis of use of energy. And it should give recommendations for improving energy efficiency with cost-benefit analysis, and an action plan also should be given. So this is the basic definition of energy audit. But even though so many energy audits are happening in the state, some of them lack some things. So we should make a perfect planning before doing an energy audit. So today's webinar is mainly focused on that, how to conduct a purposeful energy audit and tap the full potential of energy efficiency. So today we have Dr. Nagesh Kumar. He is a BE accredited energy auditor and have more than 3 decades of experience in energy efficiency. He is a mechanical engineer basically with post-graduation in energy management from National Productivity Council. He also holds a doctorate in the field of gas turbine. He was the director of National Productivity Council, Chennai, and at that time he was one of the orders for the guidebooks on energy efficiency for the BE National Certification Examination for energy managers and energy auditors. And after his retirement from National Productivity Council, he is running his own firm called Center for Energy, Environment and Productivity, and is located in Chennai. So I think he is the most apt person for talking in this topic. He has been doing energy audit for the past 3 decades, and he is a well knowledgeable person. So basically, this digital platform is provided by IIITMK. It is Indian Institute of Information Technology and Management, Kerala. So we can now move on to the webinar. And before moving on to the webinar, I will add one more point, that you can use this chat box for posting your queries. So you need not wait. You please not interfere in between the presentation. You can put in your queries in this chat box, and the speaker will be clarifying your doubts. And there will be a last session of FAQ also for clarifying the doubts if time permits. If time does not permit, you need not worry. We will be consolidating all the queries asked in this webinar posted by the participants, and we will be getting the answers from the speaker. And also, we will be forwarding this FAQ document to all the participants. And now we can hand over the mic to Sri Nagesh, and I request every participant to please switch off your camera, because if you are switching on the camera, it will consume the internet and the presentation will be breaking for you. So kindly switch off the cameras so that a continuous presentation will be allowed. So I will share. So the Nagesh will be starting the presentation now. Kindly wait. Thank you. Hello, sir.
Yeah.
We can hear you, sir. You can start the presentation.
Right. Good morning.
One more. Yeah. 1 second, sir. Sir, Mr. Jahangir, can kindly switch off your camera. Hello. Nagesh, you can continue, sir.
Yeah, thank you, Sharath. Good morning to everybody. Of course, we don't have the pleasure of meeting face-to-face physically, but at least there's an alternative. So today we have connectivity so good that we are able to discuss with each other over the internet. This is actually a boon. So this is how the technologies have evolved, the systems have evolved, and if you see, when I joined National Productivity Council in 1986, that was just the beginning of the energy audit phase, we can say. The energy crisis itself happened somewhere in the early 70s, 1973, when the first oil crisis occurred. That was the beginning of the energy conservation movement in India. And subsequently, when we joined the National Productivity Council for this 2-year course, not many of us were sure what we were going to do. We all, went into a work environment after our graduation and found it so tough that we again want to relax by doing a course. So I joined this course, and later on, after the end of the course only, I realized that it's all about saving energy. So then it was a real pleasure, because you're challenging the designer, you're challenging the operations engineer. So there's so many things that you actually come to know and also try to apply whatever you learned. So it became very fascinating in this field, and so I continued this field, and now, of course, we have seen a lot of developments in this field in terms of technology, the way we approach energy savings, the way we approach energy audit. And then we also have this mandatory energy audits where the government has legislated an act to make energy audit mandatory for some of the high intensity consumers, the designated consumers. So much water has flown under the bridge ever since this energy conservation movement started in India, almost about say 50 years back. So we can say that we are celebrating the golden jubilee year now, early 70s, and now it's
Sound is not audible.
Dear participants, kindly wait. They're having some technical issue with the speaker, and I'm trying to resolve it. Sorry for the inconvenience caused. Hello, yes, sir. The speaker had some network connectivity issues in his house, and he is trying to reconnect it. Kindly bear with us.
Hello.
Yes, sir, we can hear it.
Okay. So this issue with technology, as we just being praises technology, we saw that my Wi-Fi got cut and I'm now on the hotspot. Doesn't matter. We always seek to find alternatives, and that is also the approach towards energy audit. It's not all that easy. Energy audit is something where the designer has already built in something, and then the operations man is further trying to optimize as per his requirement. And then as an outsider, you go and try to meddle with the systems and seek improvements. It's a real challenge. So let's see, the need for energy audit is already known for those who have already seen these slides. It may be a repetition. As we see in this slide, you have a typical energy balance for the United States, where the input energy is 84% in the form of fossil fuels, and then we have biomass, nuclear, and all that constituting the remaining. So if you look at the way in which energy is used, ultimately, the useful energy, that is the actual energy required to do some work, is hardly about 8% or 9%, as you can see. So this 9% is the final work that is done. And 7% is for the manufacture of petroleum-based products like plastics and all that. So maybe this can also be considered useful in some way. But what you find here surprising is that the losses, as we use energy, there are two significant losses. This 41% is unavoidable energy waste. So unavoidable energy waste is something which happens because of the limitations of thermodynamics, limitations of engineering. So in a typical diesel engine, you will find that the efficiency of the engine is about 30%. About 35% goes into the exhaust and 35% comes out through the cooling water. So some amount of heat rejection, some amount of losses will take place. This is as per the second law of thermodynamics. Whenever you convert heat to work, it will be accompanied by a huge loss of energy. So that is why all your heat engines, be it a power plant, a diesel engine, your automobile, all these are based on heat engines, which are accompanied by a huge loss of energy. So in this, there are some technical losses, which are, of course, limited by the thermodynamics. But then there are some losses which are under our control. This is 43%. So 43% is unnecessary energy waste. So unnecessary energy waste, the simplest thing is, you, for example, an air conditioner, you set a temperature of 22 degrees. Unnecessary. We want to be comfortable. We don't want to be cold and freezing. So if you raise the temperature to 25, which is quite comfortable, you save about 10 to 12% of the energy in the air conditioner. Or if the room is open, you have an air conditioned room, the doors are open, then again there's energy. So these are all some of the losses which we will find occurring quite often in the energy use situations, either in the industry or in the commercial buildings, or even at homes. We find that there's a huge potential for saving energy for this economy. So this is what can be saved. This can be saved. Remain there, whichever country it is. So we are trying to look at this 43%, how we can save this energy. Okay. Can you move to the next slide, Bharat? Control is with you.
Yes, I will do it for you.
Yeah.
Okay.
Yeah. So this is a typical thermal power plant where we are putting in, say, 100 units of energy into the power plant. So 100 units, if you're putting, the electricity that comes out is only 30%, hardly 30%. Remaining 70% is lost in the power plant itself. This is as per the previous slide what we discussed about the diesel engine. The heat engines are always accompanied by huge loss of energy. So unless this much amount of heat is ejected, you won't be able to get this much of electrical energy output. So heat is converted to work. 30 units of energy is coming out as electrical energy. 70 units is lost. Then it comes through the wires. Transmission and distribution loss about 9%. Comes the motor, which loses about 10%. And then the coupling, little bit of energy is lost. Then pump, it drives a pump, let us say. The efficiency of the pump itself is about 25%. So there's a the efficiency of the pump is 75% and the loss is about 25%. Then you throttle, that means slightly close the valve. Too much of water is coming, we want to reduce the water, slightly close the valve. So you lose about 33% in that. Then the friction loss in the pipe is about 20%. So finally, when the water goes to the overhead tank, we only have about 9.5 units of energy. After that, we open the tap and forgot to close the tap. Then the entire 9.5 units is drained down without any useful work being done. So as you can see, the energy that we are using has traveled through lots of ups and downs, and so much of losses it has suffered on its way. And finally, just at the flick of a switch, we are able to utilize the electrical energy. Okay. So this is the electrical system as we see in a typical industry. We have the power from the distribution company coming in, then you have a meter provided by the distribution company to monitor your energy consumption, your demand and other parameters. Then it comes to a transformer. And then there's a distribution system, cables running all over the place. And finally, they are connected to the electrical motors. The motors are driving the mechanical loads like pumps, fans, compressors. So if you see this whole system, what is the energy saving that is possible? Because if you see the transformer, which is the first equipment it comes into contact in your industry, the efficiency is 99%. Very minimum scope, nothing significant. So it won't change your profit line dramatically by attacking the transformer, trying to save energy. So very minimum scope is there. Then it goes through the cables. Depending on the size of the industry, this loss will vary. It can range from less than 0.5% for many of the medium scale. If you are about 1000 kV and less, it will be now about 0.5% or even less. And maybe in a bigger establishment like mines and other places, it can go up to maybe about 3 to 5% depending on the length of your LT lines, LT to HT ratio and all that depends. So then it comes the motor. Motor, of course, if you can say this is 90%, let's say the average efficiency of the motor. So the motor is the least energy efficient equipment in the electrical system. This forms the electrical system. This forms the mechanical system. So the line is clearly drawn here. This is the Lakshman Rekha. So electrical man cannot intrude into the mechanical, mechanical man cannot intrude into electrical. So whenever there is a motor tripping, there is always a dispute. The mechanical man says it is because of electrical problem, electrical man says because of the mechanical problem. So there is always a tug of war. And this is the line which is clearly drawn. So what we can say is, in this segment, in this section, there is very little scope for energy saving. Electrical engineers may feel offended when we say they don't have any role to play in energy conservation.
Hello, sir. Nagesh, sir.
Okay.
Sir, there was a sound break in between. So what you explained in between, we haven't heard. Can you kindly repeat it, sir?
Okay.
Hello, sir. Your audio is breaking. Okay. Okay. Hello.
Sound is not visible.
Sound is not coming, sir.
Nagesh will be joining in within 2 minutes. He's trying to rechange his connection back to his Wi-Fi mode. Please wait, sir.
Okay, again, let us say sorry that there are some problems here. Some work is going on here. So anyway, now let's go ahead.
So can you now change yours? Are you able to change the slide?
Yeah. Okay, fine, leave it. Okay. Anyway, these are all things which are possibly known perhaps, and now what is meaning of purposeful energy audit? So there is a client who wants energy audit to be done, and what is his objective? His objective is to save energy, save money. Now, for that objective, how are you going to approach the energy audit? Because everything is new. As you enter the factory, everything is new, and we need to understand the process, collect information, maybe do some measurements, and then arrive at energy saving options which will be acceptable to the company. So this is a process. So in this process, and the time you're going to spend is not much. Maybe you'll have to be on level or par with the people in the plant within a few days. You should be talking in their terminology, which means it's quite a big challenge for the energy auditor. Now, fundamentally, as we want to save kWh, we know that it is a function of kilowatt, the power drawn into number of hours of operation. So you can reduce kWh by reducing the power drawn, that is a kilowatt, or by reducing the number of hours of operation. So the potential exists either for both, or either of this can be reduced, and you can reduce the kWh. So in many of these situations, when we look at an energy audit, so normally we either focus on electrical energy or sometimes thermal energy, but in our opinion, over the past for so many years we have done the energy audit, it always helps and it's beneficial to have an integrated energy audit consisting of all energy sources used in the plant. Okay, so these are the thermal energy sources, the petroleum fuels that we use, and then we also use coal for thermal energy, and in thermal energy we are mostly focused on efficient use of downstream heat carrying medium, maybe steam or thermic fluid or hot water, whatever it is, because as we know, most of the boilers have become fairly efficient nowadays. So it's not like the Lancashire boilers, which were about 55 to 60% efficient. Today we have even fluid bed boilers which go up to almost 80% efficiency, and oil-fired boilers are anyway pretty efficient. So we had to look for reduction in steam consumption. So that how to optimize the steam consumption, reduce steam consumption, so that you can save fuel on the boiler. These are the agro fuels that are used, and many types of agro fuels are used in Indian context. Everything that is burnable. So we don't waste much. We are not a wasting society. So whatever we would like to utilize it, we are utilizing coconut shell, bagasse, as we know is a good fuel, and rice husk, rice bran. So these are all some of the fuels which are used. Now let us look at, given the situation, suppose somebody is calling us for an audit, how are we going to approach the audit? So we go into the plant. So let's take a simple case of a printing and packaging unit where the operations are fairly simple, so it will be easy for all the participants coming from very different sectors to appreciate how energy audit is done and how do we approach energy saving opportunities, how do we identify energy saving opportunities. So this is a small printing and packaging unit. So as we go into the plant, what is the first thing that we need to do? Of course, you shake hands with the head of the plant and get in touch with the people concerned. So preferably, we start with an opening meeting. An opening meeting where representatives from different departments are there, the head of the plant is there, and we explain the objectives of the audit. So then you get to know everybody at the same time, and also when you go personally to every department, the cooperation is ensured. So you start with maybe a short opening session, maybe 1 hour. Tell them what the audit is what we are proposing to do in the audit, and give some examples of successes which you have achieved in the earlier audits. So it gives them some confidence, and also you can ask them about what are the various energy saving measures that they've already undertaken, so you know what is the level of the plan. So with that we start, and then we look at the electricity bills, collect data, and basic data are collected, and then you go around the plant. So for example, in this case, this is the electricity tariff. So this tariff, you find out what is the tariff category and what are the features of the tariff. So it's a two-part tariff, meaning that you have to pay for the demand, sanctioned demand, 450 kVA, demand charges is 250 per kVA. So energy charges. So these are all the things that you should be collecting in the initial stage itself. So whatever possible you can optimize in the tariff, that can be done. So understand the tariff first, and then so let's see how the demand. Let's say they're going to pay a huge amount of money for the demand. How the demand is varying over different months. So you find out the variations. So it's going up and down, and probably you can relate it to the production later on. So here it is, we're just looking at the demand. And if you see some abnormalities, some ups and downs are there, then you can actually do a daily load curve. So you ask somebody to take readings every 1 hour of the kVA, or kWh every hour for 24 hours, and then you plot a load curve like this. So a load curve is something which will give you how the load is varying over a period of 24 hours. So probably you will have something like this. So 24 hours, so load curve may be like this. So maybe this is a night shift, load is less, and during the morning shift, load is fluctuating like this. So you can see why these peaks are occurring, and see if we can bring down the peaks by rescheduling operations, by modifying the operation. So potential has to be explored. So we cannot come to a conclusion, but this shows that there is a potential. Can we reduce this peak? Why the peak is occurring? So we start with this. Demand reduction is not actually an energy conservation measure. When you reduce kVA, it has nothing to do with kWh. So demand reduction is good for you because it will reduce your demand charges. It can reduce your electricity bill, no doubt. But it is not going to reduce your kWh consumption. Doesn't matter. Our objective is to reduce the electricity bill, either from through kWh or kVA. So we're not concerned. So this is a load variation, as you can see. So we find that there is a potential, and then immediately we ask for this data. Put somebody on the job and ask them to look at the meter every 1 hour, find out what is this kWh. So it can be kWh or kVA. We just want to know the pattern. So you see a plot of this gives you a load curve like this. And here there are some peaks which are occurring, obviously. So these are the areas. You have to look into the process and see what equipment are probably contributing to this peaks. And suddenly there is a dip here. So why there is a dip? So this analysis will be quite useful if you want to bring down the demand. So in here, bringing down the demand, again, you have to see whether it will serve any purpose. Because in some electricity boards or discoms, you have to pay for 90% of the contract demand. Whether you use it or not, minimum 90% is the billable demand. In some cases, it is 100%. So it varies. So if you are anyway less than 80% or 90% of the contract demand, it doesn't make much sense to do a lot of work to bring down this demand. Anyway, you will be paying for the minimum billable demand. So that is why the tariff clause, what is there, is important. And kVA, as you know, it can also be reduced by improving the power factor. So as you improve the power factor, the demand reduces. Improve is equal to kVA, your demand into power factor. This is something which is often debated, whether power factor improvement will reduce energy consumption or not. the power factor, cos phi. Now, what is this kW? Who decides the kW, or what decides the kW? So we have a motor, and then we have a pump. Okay, so then the pump is pumping some water into the process. Now, this kW drawn by the motor. What decides the kW drawn by the motor? It's not the motor which says I will supply so many kilowatt. So it is not the pump which says I will supply so many kilowatt. It is actually the demanded water. How much of water is required here? At what pressure? The pressure of water, the quantity of water decides the kilowatt delivered by the pump. Then the efficiency of the pump comes into play. So you take this efficiency factor, then what is the kilowatt demanded from the motor is decided by the flow, pressure, and the efficiency of the pump. Then what is the actual power drawn by the motor? Depends on the flow, pressure, pump efficiency, and the motor efficiency. So these are the factors. This is how there is a cascading effect, and the starting point is unfortunately not in the wire. Yeah.
Hello, sir.
Okay. Yes, sir.
Your voice breaks in between, sir. Can you kindly repeat that point, sir?
Okay, let me just, my voice is breaking, huh?
At that particular point.
I think my Wi-Fi is back. Let me kind of change back to Wi-Fi.
Yes, sir. Please, sir.
Can you hear me, Sharat?
Yes, sir, we can hear it.
Yeah, I'm back to Wi-Fi. Hope it continues. Right. So this is what we were looking at. The kilowatt drawn. Whether power factor can reduce my kilowatt or energy consumption. And as we said, kilowatt is decided not by the motor. It is decided by the final end use. How much water is going to be used at what pressure? This decides the kilowatt delivered by the pump. And if you take the pump efficiency into consideration, this is the kilowatt demanded from the motor. And of course, if you take the motor efficiency into consideration, this will be the kilowatt drawn by the motor. So in this, whether it is power factor, if you're going to improve the power factor, whatever be the case, the kilowatt will not change. So when you improve the power factor, the kVA, the current will come down, but kilowatt will not change, it remains constant. So improving power factor is not going to reduce energy consumption. So this is one thing that maybe some people may claim that, when you reduce the amperes, the I squared R loss in the cables will come down, all that logic will be put forth. But if you see, it is hardly a few watts will be saved. The meter cannot even recognize that distribution loss reduction by improvement of power factor in an industrial setup I'm talking about. Okay, so this is one thing which needs some clarification, and then components of electricity bill. So as we see, okay, what is the bill consisting of? The energy charges is accounted for 72 lakhs. Demand charges account for 13 lakhs. So now we will see what is the impact of or intensity of demand charges, intensity of energy charges in a total electricity bill. So this gives you a fairly good idea as to know where the focus should be. The most important thing, as we have seen in many of the audits, though not much attention is paid to this, is the energy balance. How much of energy is going where? This is important. So in the earlier days, there was no individual metering for different departments. But today's metering has become so easy and affordable that many of the industries have been able to segregate the departments and provide individual meters for different departments. So as a result, monitoring becomes easy. Now here, if you in this pie chart, the printing machine section, the printing machine in this factory is consuming 51%, and followed by post printing drives. So these are all the different departments: plate, baking, compressor, so air conditioners. So all these different departments are there. Now again, why we are using this is that our focus should be more on areas where the energy consumption is high. For example, we would like to focus here. We would like to focus here. Sometimes what happens, the energy consumption may be very high, but potential may be low. Here, for example, printing machine air conditioners. It is not very significant compared to this. It's only 11%, but the potential may be high. So this alone cannot give you the focus area, but you'll also have to look into the potential possibilities for energy saving in different areas of operation. And together with this pie chart, you can fix the area where you need to concentrate or focus more.
Hello, Nagesh sir, there is a query came from one of the participants. If an industry is not having individual metering, then how can we draw the energy balance?
Yeah, if you don't have individual metering, now at least you should have a portable power analyzer or power meter, something which you can get it for about under 50,000 rupees. There are meters available, a portable meter. So what we do is you find out the kilowatt, instantaneous kilowatt drawn by the different motors in every department. So kilowatt hours, kilowatt is known, and you also find out what is the number of hours. So number of hours of operation. So roughly you get to know what is the kilowatt hours in each and every department. So you don't have to have a meter, of course. If you have a meter, monitoring becomes easy and continuous. In the absence of that, this is the next best possibility. Okay.
Will it be an energy balance or an energy breakup?
Sorry?
So is it energy balance or energy breakup? What you have mentioned?
Yeah. I mean, it doesn't matter. Rose smells as sweet with any other name. So whether it is balance or breakup, it's all be the same. So how much is the total energy coming in? So you are accounting for that total input energy, where all it is going, how much it is consuming. So sum of all the the energy consumed by different departments should be equal to the energy coming through your grid meter. So you call it a breakup or balance, it doesn't matter. Yeah, any other questions?
As of now, related to this, no, sir. We can move ahead, and in the end.
Okay, so anyway, you keep your questions reserved, so we'll spend more time on questions.
Okay.
Yeah. So now the energy conservation. So we have done this breakup and we are going into the plant. We see the plant, observe the operations. One of the most important thing is as an energy auditor, we don't, many of the plants we find that as soon as you go for a walkthrough, there is always an electrical engineer accompanying and he will take you to that switch yard. So you go to the switch yard, hot sun. So then he shows you this is the vacuum circuit breaker, ACB, VCB, and all that you see in the transformer you see. But what for? Then what do you do with that? Then he takes you to the panel room. Then he says we have so many meters here, this meter, that meter, this relay, that relay, and all that. But
Thanks.
Can you repeat?
No, sir.
Yes.
Interruption.
Okay. So, yeah. So, what do you find? What do you gain by, gazing at the transformer, by gazing at the motor, by gazing at the panel room, switch yards? Nothing. So, the best approach, of course, what we are trying to tell is some kind of approach which we find is probably the best, but there may be better approaches. So in our experience, from our experience, what we can say is the first thing that you should do is start with the raw material. Don't start with energy. Forget about energy. As an energy auditor, your starting point is not going to be energy. You start with the raw material. So raw material coming into the plant. What is the first step? So maybe as a pulp and paper plant, it goes into the pulper. So from pulper, it goes to different cleaning operations. Then it goes to the wire part. Then the paper is made, it makes reams, and then the cutting section. So you take a walkthrough and try to understand what is happening to the manufacturing process. Raw material to final conversion. At every stage, what is the change that is happening? So you become fairly acquainted with the process. This is fundamental to a good energy audit. So only if you know at least you don't have to become a specialist in that short time, but at least you should be acquainted with the process. So any measure that you're going to suggest should not interfere with the process, number one. And also there are a lot of hidden opportunities. This is why we are saying that this process-oriented approach is crucial. See, for example, if there is lighting is the lights are there everywhere. Visually, you can see that nobody is there in the room. Lights are on. Then you find that as an obvious energy-saving measure. Switch off the lights. Very simple. By looking at it, you can tell that. There's a steam leak. Also, obvious. Visually, you can see that there is a wastage. There are many things, idle operation of the motor. Some belt conveyors are on, no activity, idle operation. That's also visibly you can see. But there are hidden opportunities where the potential is substantial. Say a pump, for example, simple thing is a pump. What is the efficiency of a pump? As we have seen, maybe maximum it could be 75%. This efficiency is on the nameplate. Motor efficiency is 90%. That is also on the nameplate. Yes. So the 90% efficiency for the motor, you can take it for granted. it is going to be 90%. Because if you see the characteristic curve, efficiency versus load of the motor. So this is the efficiency and this is the load. So the efficiency of the motor does not change much with respect to load from 50 to 100%. So this is the efficiency curve. So you see this is 50%, this is 100%. So efficiency remains the same. It's not affected much. But in the case of a pump efficiency curve will be like this. So this is the max, there is a maximum efficiency, say 78%. This is the maximum efficiency of the pump. That is at the operating point, best efficiency point. If you're operating, the pump efficiency will be 50%. Let's say about 100 meter cube per hour flow. The pump is operating. So the best efficiency point you're operating. Suppose you want lesser flow, you want only 70 meter cube. Then what happens? This pump efficiency can drop down to 40%. But if you see a pump and a motor, so when you go back, you take a look at the motor and the pump in your industry, whoever is working in the industry or for the energy audit. So there's a pump, the motor, something is happening, some water or some liquid is being pumped here. So everything appears pretty normal. So motor is operating, pump is operating, and all operations are fine, product is coming out, everything fine, no problem. So the production man says the pump is very efficient. It is giving him whatever he wants. The operations are enabled. Operations are successful. But at what cost? We don't know. So unless you measure. So here, that is why sometimes measurements are pretty useful. It has to be again purposeful. Only when there is a need, you do the measurements. We have seen many times, in fact, we also used to adopt this practice. As soon as you go to the plant, start measuring all parameters of the motor. Kilowatt, kVA, voltage, ampere, power factor, everything. And finally, a huge maze of data is there. You don't know what to do with that. Nothing will come out of it. So you decide what you will measure when a measurement is required. No point in simply going around measuring all motors that are on. So now here we want to know how much should have been the energy consumed for maybe pumping some water up to this level in this tank. How much is the actual energy? That we are interested. So now you put your power analyzer, power meter and measure what is the kilowatt drawn. Then if possible, you measure the water flow. This is, see, what we are trying to say is almost near ideal conditions. Ideal condition means as you go to the plant, okay, the motor is working, pump is working, everything is on. But as you say, kilowatt measurement is fairly simple. So electrical engineers have made things so simple. The transformers are efficient, motors are efficient, the measurement of power is so efficient, you don't have to struggle. But measuring water, how do you measure this water? If it is like a simple filling the tank like this, it's okay. You measure the level over a particular time period, you know what is the flow rate. Otherwise, how do you measure? You don't have flow meters for every pump application. So then, of course, you will have to go in for ultrasonic flow meter, which is again such a laborious process. It has not been made so simple. Mechanical measurements are so complicated. Unlike electrical measurements, you open the panel and put a tong and touch the voltage, you get the kilowatt. Very simple. But mechanical measurements, we say simply, okay, you put an ultrasonic flow meter, measure. But you see the amount of preparation that needs to be made for putting this ultrasonic flow meter. So many conditions are imposed. There should be a straight length, 10 times the diameter. Pipeline should not be rusted. Inside pipeline should not be scaled. Then you file the pipe. Then you hammer the pipe to remove the scales. Then you put the sensors here with the gel. then finally you don't get reading. So you spend 2 hours, 3 hours sweating in this place, and then finally nothing happens. So it is quite tricky. I mean, this is not that it is always like that. Sometimes, of course, the pipe is clean and almost like a laboratory condition. Then, if of course, ultrasonic flow meter does give readings. So assuming that somehow we are able to manage the flow rate and the pressure, then we are able to find out what is the efficiency of the pump. We are interested in finding out what is it. Then we find that in this case, the pump is throttled and it is operating at 40% efficiency. So we have measured the power, we measured the flow, we know the pressure inlet outlet, and from that we find the pump efficiency, we find it is only 40%. This we would not have known if we are not measured. So this is a hidden energy saving potential we are talking about. If you don't measure nothing, no problem. The process continues. The process is not going to be disturbed. But when you want to find out how much is the energy loss or the potential for energy saving, you need to measure and find out, dig out the energy savings potential. Right. So in this case, what were the energy saving measures? So in the printing press, of course, here in this particular DISCOM, they were providing incentives. So there was a chance to improve the power factor. Nothing extraordinary in this. Now almost all the plants are maintaining near about 0.99. And in this case, there was a problem with some of the capacitor banks. So this is again, sometimes a faulty capacitor bank, for a brief period, the power factor goes down and the demand shoots up. So for that entire month, you have to pay for that demand. So that means a constant monitoring of your power factor helps. Here is a very strange case. Actually, yeah.
One doubt from participants. What method if ultrasonic flow meter is not there?
What method?
For measuring that. If ultrasonic flow meter is not there, what another method can be used for measuring?
Yeah. So you have to find out some innovative methods yourself. Technologically, ultrasonic flow meter is an advanced technology, no doubt. So the meter itself costs about 3 to 5 lakhs, anywhere depending on the brand, and still, you're not guaranteed that you will get accurate results. Some values come, of course. Sometimes there is no signal, no values come. Sometimes some values come, and sometimes maybe the values are right, sometimes they are not. So there is always some questionability in ultrasonic measurements. In the absence of ultrasonic flow meter, what we can do, so you can actually check the level difference. Suppose you are drawing the water from a sump. Let's say this is a sump where you are drawing the water from. So for a brief period, you see what is the level, water level initial, water level final. So you know the dimensions of the tank, a simple mensuration. And you find out what is the amount of water pumped or what the time taken. So this is one way. Or in the discharge side, you see the tank level difference. That is another possibility. So if this is a heat exchanger, so some cooling water is pumped. We want to know how much cooling water is going through this. Process side, there is a metering, assuming. So it is going at some 80 kgs per hour, some product. And once we know from the process side what is the heat, from the heat balance also we can find out indirectly by calculation. So the first thing is measure wherever possible. If you can't measure, calculate using, like as you said, the heat balance, MCP delta T here, this side, if you know the process flow rate, then we know the temperature across this heat exchanger. Then you find out what is MCP till 30 equal to MCP till 30. Then you will find out mass of cooling water, which is the pumped quantity of water. So if you can't measure, to calculate. If you can't calculate, you can guess, estimate. So estimating means, okay, maybe, so you suppose in case you have a pump characteristic curve, assuming that you have very good document system where whenever a pump vendor supplies a pump, you ask him for the characteristic curve and you keep it neatly in a file, well stored, then you take out the pump characteristic curve. So this is the pump characteristic curve. Then this is the power curve of the pump. You measure the power, motor power, multiplied by the efficiency, gives you the shaft power to the pump. So this is the shaft power. So we know what is the shaft power. So at this shaft power, corresponding to this, what is the flow rate? So the pump power versus flow. This can be one method of estimating the flow rate. So you know what is the flow rate here. So in the worst case, you have to guesstimate. And guesstimate means, okay, roughly perhaps something is going on. It could be around 20 meter cube, it could be around 30 meter cube. So guesstimate, but ultimately you decide what for. Why should I do all this? If I can't measure, if I can't estimate, if I cannot calculate, if I can't even guesstimate, don't do it. Best thing is not to do it. Don't trouble yourself. We are here to enjoy life, not to put ourselves into trouble. So whatever is possible, do it. If not possible, don't do it. So as simple as that. Okay, so this is, yeah, we were discussing about this, increasing contract demand. Normally, any plant wanting to set up an industry establishes a contract demand with the distribution company. And normally, it will be much higher than what their actual requirement will be, because they always look at the future expansion, additions, all that. So this used to be one of the most ubiquitous cost reduction measure in some of the earliest energy audits. If you take maybe about 20-30 reports of the energy audits carried out between, say, in the 90s, you will find the first saving measure will be reduce the contract demand. So reducing contract demand, then you say so much savings, so everybody is happy, but nobody is going to reduce the contract demand. It will remain on paper, it will remain in the report, because once you reduce the contract demand, getting back that is such a big problem. So nobody wants, even if it is going to be involving some additional expenditure, additional bill amount, doesn't matter. So they will continue to maintain a higher contract demand. In this case, what happens, the contract demand is there, they have gone for expansion, of course, and it is shooting up. The production levels have gone up, new machines have come, it is going up, and to compensate for, so you, of course, you can exceed the contract where you can pay a penalty. If you keep doing that quite often, your power supply can be cut. So in order to avoid that, this company was using DG sets. DG set, as you know, the cost of diesel is almost 70 rupees per liter now. So if you operate a DG set, and depending on the load, so normally you will be operating 50 to 70% of the load, which means it may give 2 or 3 units per liter. So 25 to 30 rupees will be per unit. It's a huge waste. So first thing is for them to increase the contract demand, and so by doing this they could stop some of the diesel generator operation hours. Then avoid rarely utilize higher DG set after increasing the contract. This is the process. So the savings is going to be, and they have hired the DG set. They have a DG set that is not sufficient, so they have hired one more DG set, and they're paying the hiring charges. And whenever the demand is likely to go up, some new machines are going to come into operation. They operate the DG set. So in the previous financial year, this was the amount of diesel consumption used for that higher DG set. So that can be avoided. So actually, so you have to have a holistic outlook as you go for the audit. You're not going to see things in isolation. You will have the entire mapping of the plant. So you have to link one to one. Suppose we are now, this is the printing shop where the printing machine is there, 8-color printing machine is there in this room. So this is air conditioned. So when you're here, you should know what is the transformer rating, what is the tariff, what is the energy consumption, maybe some compressed air is there. So at the back of the mind, you should have mapped the entire factory. It should be there in the back of the mind. So there may be linkages from here to there. Okay, so here we have a printing machine. So, and this room is air conditioned. So you have to calmly observe what is happening. So don't rush and measure the power consumption of these air conditioners or these motors running the machines. Nothing to worry about it. Simply observe quietly what is happening. So how the papers are coming, how the ink is being poured, how the screens are being changed. So all these things you keep on observing. And now here we see that this room is air conditioned, and as you keep observing how we can reduce the energy consumption for this air conditioner. So some measures were identified. Basically, when we are looking at air conditioning or refrigeration, our objective is to minimize the heat load. How we can minimize the heat load first? So in this room, there are two air conditioners, 11 TR and 5.5 TR, which is in operation. And the problem here is energy is secondary, but all these printing inks, they're all with volatile organic compounds. And as we know, in a split AC, there is no exhaust. The whole room is full of volatile organic compound. Very difficult to stay inside the room. And this is split air conditioner. So no exhaust. So the ink evaporating. Room full of VOC. So this is one criteria. And when there is a change in the product, screens are going to be changed. The machine downtime due to change is 10 hours per day. So as they clean the whole rollers, screens, the entire process takes 10 hours for the next batch to begin. So every day there is a downtime due to change of 10 hours per day. But what we observed, even during the downtime, as they were cleaning up the rollers, machines, the AC was on. Why the AC is required, first of all? See, this is where the why analysis comes. Okay, printing machine is there. So why at all AC? Then they say some panels are there, and then the gap between the rollers, fine adjustments here, all this requires controlled temperature. Okay, fine. But when the printing is not going on, you don't need to be maintaining a controlled temperature. So the first question was, okay, one batch is over, next batch when it is going to come, it is going to be 10 hours. So in between, can we switch off the AC? So it started with that. When the machine is not in operation, the ACs can be switched off. Now, operators will feel suffocation. That's what they say. there will be suffocation because the temperature will be high inside that room, completely enclosed, and this VOCs keep circulating. Then we said, why don't you provide an exhaust fan to exhaust the stale air during the downtime period? Now, during this off period, 10 hours off period, there is no emission of VOCs, but the existing VOCs continue to circulate. So what you do is you put a fan and exhaust all the VOCs. So what was done next was we had to break open the one wall, and like this here, you see this is the wall, and this is the air conditioner. Now this wall was broken open and then a fan was fitted. This fan will be on once one batch of printing is over, and they're going to make way for the next batch, change of rollers and all that. During that time, the AC will be switched on and the fan will be in operation. So this will, the two things. One is AC we're able to switch off. The existing VOCs are able to be vented, and also it maintains a stable temperature inside the room. There is no heat within the room as the exhaust starts operating. It also chills the room a little bit as to keep the other side, on the other end also the door is kept slightly open, so there is a cross ventilation which leads to maintaining the temperature within the this room, and VOCs get exhausted. Now, what is the benefit of this? So an exhaust fan is provided. As you can see, the energy savings from this is almost about 60,000 units per annum. And in terms of monetary, it's about 3 lakhs. For an exhaust fan, opening the wall and then putting an exhaust fan is hardly about 20,000 rupees. So the payback period is 1 month. So basically, you have to observe the process, what is happening. And one full cycle is preferable, because if you've not been there for the entire day, then we would not have known about this downtime and 10 hours changeover time and all that. So accordingly, your ideas for saving will vary. So in a simple printing press, it can be quite a significant saving. 3 lakhs is quite a huge saving for them. And in the same room also, what was happening in this room, there was also some heaters in this right side. You will find that some heaters were also provided, which of course were taken out. So you'll have to see what are the unnecessary heat loads in this room. Now, what are the unnecessary heat loads? So one is, of course, the machine heat. Whatever the motor, so all these motors, let's say there are about 5.5 kilowatt motors, some 6 motors are there. So it's drawing 30 kilowatts of power. 30 kilowatts means 30 kilowatt into 860 kilocalories it is emitting every hour. So that 30,000 kilocalories or whatever, as it comes out, that is a major heat load that this air conditioners need to handle. So additionally, there are some other unwanted heat loads, as we said, the heaters here. Then you see this window. It's a glass. So throughout the length and breadth of this room, you have almost 50%, more than 50% of the area is glass. And outside this room, it's quite hot. So hot air is entering this room through this glass. It's almost like producing a greenhouse effect into the printing room. For this Oh, okay, there are several suggestions. Somebody said we'll put a, that heat resistant or, heat resistant panels or double glass. So anything can be done, but the objective is that we should prevent this heat, which will further reduce the load on the air conditioner.
We have some questions.
Yeah.
Is it okay to throw out the VOCs to the atmosphere, considering the pollution? It's one of the questions. And the next question is, will functioning of AC not get affected by the exhaust fan? Because there will be some cooling loss in the exhaust openings. And also, while calculating the savings, the power consumption of the exhaust fan shouldn't be considered.
Okay, now the first question is, we are simply throwing away this VOCs into the atmosphere. What is the impact? If it is not thrown into the atmosphere, what would have happened? The operators working inside that packaging plant, they would have consumed it. So they would have acted like scrubbers. All the VOCs would have been consumed by them. Now we are throwing into the atmosphere. What is the extent to which this VOCs will have an impact? Because as you throw it to the exhaust, there is a lot of dilution that takes place. Within the room, there is a concentration. It's a concentrated environment with VOCs. When you put it outside into the air, it gets diluted. And of course, we don't have standards for VOCs from these kind of printing machines. So it is assumed that these VOCs, that they are exhausted out, will get diluted with the atmospheric air, and it may be below detectable limits if you put an ambient air sampler. That is number one. And second thing is the exhaust fan is not going to be in operation when the production starts. So actually the plan was like this: when the production starts, VOCs will come out. There is an opening now. At least exhaust fan, even if it is not in operation, there is an opening through which VOCs can still travel. The other option suggested was every 1 hour, 5 minutes, the exhaust fan can be operated. So it may, of course, result in a little bit of energy consumption, a little bit of increase in energy consumption. But when you close all the openings and operate the AC, and inside you are suffering with the VOCs all around you, that is not energy conservation. The energy conservation does not come at the cost of production, at the cost of quality, at the cost of comfort, and this is at the cost of safety. So that is more important. So this particular case is quite unique, and safety has to be the first priority. The work environment, occupational health and safety. So the exhaust fan will run for about 5 minutes in an hour, even when the production is there. So which will help in eliminating the VOCs from the room. And third is, what is the amount of power consumption for an exhaust fan vis-a-vis an air conditioner? You switch on the air conditioner, we run the exhaust fan. Exhaust fan is hardly about 400 watts, less than half a kilowatt. When you run the AC, it is 11 kilowatt actually, the operating load. So it is not that we want to conserve all the energy. So we have to, of course, necessarily use some energy and ensure that we have a decent work environment to work on. Okay, so similarly, there is one more 6-color printing machine, the same measures apply to that also. And here, very funny thing has happened. So they actually make cartons. So cartons for packaging, and Here, if you see, the whole shop is involved in making those cartons from the printed rolls. Come here, then there's cutting and all that. Then they make these carton boxes for packaging. So it's a huge shop, and these are the lamps which are there. If you see, this has come about because they found that the entire place is getting heated up during summer. The entire place is heated up, and workers are not able to work productively. So what they have done is they have provided an insulating layer here. The complete roof is insulated. So as a result, of course, temperature has been controlled. Reasonably good work environment is there, but the openings have not been provided for allowing natural light, which has resulted in keeping these lights on even during the daytime. So this is one of the things that is observable in this printing press. So what they need to do is they need to cut open the insulation in a few areas and provide that translucent sheets to allow natural light to come in. So the printing industry itself, it's a small industry, as we said, 500 kV of demand, and you will see the kind of saving potential that is there with keen observation, critical examination, and looking at alternatives. Yeah, this is that a fountain solution chiller. There's one more chiller here. The printing machine is here. As I said, that heater is on this side. This is actually a chiller for keeping what is known as a fountain solution, which is used in the printing. So an entire chiller is kept inside the air conditioned room. So what happens? It is taking the, it is chilling the water. Then the refrigerant goes to the condenser heat load. Entire heat load is coming into the plant again. So this is a unit chiller. So this can be kept out. Only that you bring a pipe inside, the fountain solution can come inside. Otherwise, this condenser part can be kept outside of the room to avoid the heat load, to minimize the heat load. So basically, we need to see the root cause. Why air conditioner is required? When you start from that, what are the heat loads? What can be avoided? What cannot be avoided? And yeah, here in this small chiller, what we had seen earlier, this is 1.5 TR chiller. Total heat liberated is this much. So by keeping that, you save, of course, quite significant. In an annual basis, about 80,000 rupees is quite good for a printing industry. So this is the printing machine room. We are reducing the heat ingress by identifying all the heat loads that contribute to the heat load. And this is the glass, the side glasses, heat resistant film, they said they'll go in for. And that is going to save them about 60,000 rupees. So the approach is the same, irrespective of the type of industry, whether it is a cement plant or a steel plant or a power plant or this printing press. We are only looking at the energy audit approach. And also, this air conditioners, why it should be continuously on. So let us take a look at the atmospheric ambient temperatures in this place. So as you can see, in some of the months, especially from November to say March, night temperatures are quite low, less than 25 degrees. So this particular November, December, January, February, 5 months, night temperatures are less than 25 degrees. And we want only 25 degrees inside that room. So why operate the air conditioners? So during night time, when the temperature reaches 25 outside temperature, you can have a control. When it reaches 25 degrees, you switch off the air conditioners and operate the exhaust fan. So that is a concept called free cooling. So you have a sensor. So inside the printing room, you have the ACs, and what you need to have is a sensor which will sense the atmospheric temperature. Then you have an interlock with this air conditioner and interlock the exhaust fan. So once the temperature reaches 25, outside temperature is 25, inside temperature also what you know is 25. Why run the air conditioner? Switch off. Then the same interlock should operate this exhaust fan. Exhaust fan keeps operating. So this is the free cooling that they get during some portions of the year, especially at night. And this is a big saving, about 6.6 lakhs for this. This is a huge saving. These things, for these things to actually get implemented and to make it work, we need to break the mindset. See, all the plant people, production people especially have a huge mindset that we have been doing like this for the past so many years. And that mentality has to be broken. Otherwise, it's very difficult to convince them that this logic will work. So it requires also some training to the operators, to the people in the production shop. What is the significance? Why we are doing? So it takes a little bit of effort. Not that easy. You switch off the AC and you're going to switch off the AC. It's not going to happen. Even at home, it is not happening. So we are telling people at home we should keep 25, 26. Okay, it doesn't work. Children, they keep it at 18 degrees and put a blanket and sleep. Outside temperature is 45 degrees. Inside they keep it at 18 and put a blanket and sleep. So it needs a lot of effort to change the mindset. That is one thing which is a barrier for implementing many of the energy saving measures. But in this case, of course, since the management was very progressive, they took a decision, they took trials, they took immediate decisions, they were able to implement it. And here also, so the air conditioners, the plate making room, so where air conditioning, what needs air conditioning? So only that you air condition, provide a partition, minimize the air conditioning load. And this, not much, but still for printing industry, it is quite a significant saving. This is a straight case. I mean, there is nothing to discuss. When you reduce the pressure of the air in the compressor, the power will come down. So anybody gets a checklist measure, a menu card measure, reduce compressor air pressure. So you don't have to think about it. You only have to look at the meter, pressure gauge, see what is the pressure setting, loading, unloading. So they're operating between 8 to 10 bar, which is pretty high. So all you need to do is to reset the pressures, loading and unloading pressures, and take a trial, because everybody wants some kind of a convincing. So they're not going to again easily accept it. So we gradually reduce from 10 bar to 9 bar, 9 to 8, 8 to 7. So then we'll see what are the critical areas where compressor pressure might matter. So observe those areas closely, whether functionality is not getting affected or not. Then you go for this setting, 6 to 7. Below 6, of course, some of the critical equipments they're not able to handle. So we set it at 6 and upper pressure at 7. So this is again quite a huge saving. Then we have, okay, this is also again another mill measure, VFD for an air compressor. Today, many of the air compressor manufacturers themselves sell the compressors with the VFD. So the retrofitting has its own problems because uh, the person here has to contact a manufacturer of VFD, and then some understanding is required for the VFD person about the compressor, and that becomes again a bottleneck. So if there is a possibility buy an air compressor already fitted with the VFD from the manufacturer, makes things easier. But in this case, they already have a compressor. So they can, of course, go for a retrofit option, provide a VFD. Only thing, you need to have a pressure sensor. The advantage with the VFD, the compressor, is in the existing conditions, they're going to have a pressure bandwidth 6 to 7 bar. So this is the compressor will load at 6, unload at 7. If you have a VFD, you can operate between 5.98 and say even 5.9, depending on the transducer's sensitivity. You can keep it at 5.99 to 6.01 or 5.9 to 6.1, depending on the transducer you're going to use. So if this is the case, at 5, when you put a VFD, at 5.9, the VFD will increase the speed. 6.1 VFD will reduce the speed. So the pressure is constantly maintained. Instead of bandwidth of 6 to 7, a constant pressure of 6 will be uniformly obtained. Okay. So this is another option that is available. And yeah, there were other things which, of course, they couldn't take a decision. They wanted the discussion with their head office. So we kept that in abeyance. And also this insulation. These are all some minor things, but still they matter. Cumulatively, they can lead to significant savings. The fountain solution tab that we have seen earlier inside that printing machine, it is brought out. It is brought out, and then the whole tank, which is containing the fountain solution at about 8 degrees centigrade, it is not insulated. So insulate it, but it will reduce the energy consumption of the chiller. And in the plant itself, this is a mistake which many of the factories do. The plant is so beautifully designed with cross ventilation. So if you see a typical factory shed, it will be like this. So there is a window here, right on the opposite side you have a window here. So what happens, there's a cross ventilation. So free flow of air is there. And if you have a north roof sheet, that means the air, there is an opening here at the top. And suppose if you provide some turbo vents and all that, then the hot air will tend to go up like this. But however, for worker effectiveness, this cross ventilation is required. Many times we find that these windows are getting blocked by storage of materials, which is leading to a hot environment inside, and that is why they went in for the roof insulation. This company went in for roof insulation because all the openings were blocked by storage of materials, and the entire shop floor becomes hot. So this is one area where some focus is required to ensure good work environment. So these are some minor details which we will skip. So this is a baking oven where the screens are baked. So whatever screens we have seen in the rotary printing machine, when the screen is made, they'll be baked about 200 plus degrees centigrade in this oven. And this oven, again, if you see, this is kept inside an air-conditioned room. So the entire heat that is coming out of this is taken, the heat load is absorbed by the air conditioner. So you can provide a partition and isolate it and provide exhaust fan. So you provide an exhaust fan here and you isolate it from the rest of the room. One major problem this company had was they were getting rolls and rolls of this cotton paper from the paper mill, and it comes with a wooden packing. So much of wood had to be disposed. They were paying money for disposing this wood because it was occupying so much of space inside the factory. They were paying money to the contractor to take off this wood, the packaging wood. So now, as we go around the plant, we have seen the different departments in the plant, and we go to the canteen. So in the canteen, they are using firewood for the boiler. So the question was whether this can be used in the boiler as a fuel. It can be used, but some changes had to be made in the combustion system. So we had to have a wider opening for the boiler in the canteen. So slight modification of that. So this wood went into the boiler in the canteen. So they stopped purchasing firewood. The entire canteen now is met with the waste that is coming out from this, the waste wood that is coming out from the packing. And so they're able to boil rice, dal, and other cooked vegetables using the steam. So they were incurring some costs. Now they are saving from firewood. So it's a benefit in both ways. So these are the wastages. If you see, of course, when you're doing an energy audit, this may seem to be outside the purview of energy audit, but still, there is an energy content in this waste. So a lot of energy has gone into making some product, and of course, there will be some wastages that will happen. So what happens is they make cartons, and in the making of cartons, they need to punch these kind of openings, slots. Like for example here, this is one carton, and in this carton, they have to make a punch here, remove this material, carton material, and put a polythene sheet on this so that the color of the product inside is visible outside, as we see in the market. So what happens to these punch? So already a lot of energy and material is there, and then the resources have gone into making this, and then you have punched it, and then you're going to throw it out. You're going to throw it out, and it is going back to the paper mill again to get pulped. So it'll become pulp, and again carton paper will be made. So instead, we are looking at, is there some use for these kind of waste material that comes out? So this itself will be maybe in few tons per month. So probably this can be used as a price tag in some of the garments or some other accessories. So, and this can be also used. So you cut out this portion, and then this can be used as labels. So finding alternatives for wastes, because there is energy content and there is a resource. So without getting used, it has come all the way from the paper mill. We have done some modifications to the paper, put some resources into it, then we are discarding it again back to the paper mill. So it is against the concept of circular economy. So we should try to find some use for this and put it to use. Solar water for the canteen is, of course, it was an additional thing. Now today with the vacuum tube collectors, you get good hot water, even if the water quality is bad. If you have borehole, they had borehole water. Still with the high TDS borehole water, they were able to heat the water to 90 degrees. So The renewable energy itself, of course, we've been talking a lot, but it cannot replace the concentrated energy that we are using. See, if you want 10,000 kilocalories of heat, it is available in just 1 kg of oil. 1 kg of oil is just like maybe 2 or 3 cricket balls. That size can give you 10,000 kilocalories. But same 10,000 kilocalories, if you want to get from solar heater, you may need maybe about 10 to 12 square meters of space. So there are limitations using renewable energy. It cannot wholly replace the conventional energy that we are using, but it can supplement whatever energy sources we are using. Right, so that was about the printing machine, and that's a fairly straightforward audit. Again, observation, critical examination, and also go into a little bit of lateral thinking, discuss with people, take trials, implement, show the results, and then the audit is over. So that is a typical case, a small case, but the same approach is what is required in other types of plans also. And many of the cases you find that some of the industries are short on basics. So we went to one of the industries which are making some special metal powders. So the metal powders is in the form of a liquid, and that liquid slurry, they make a slurry out of that mixture of metal powders, and it needs to be dried so you get powdery material. So this goes into a tray dryer. This is a tray dryer. So a lot of trays are there. The slurry is poured into this. So in this section, if you see this, these are the trays in which the solution slurry is poured, and hot air will go inside this and remove the moisture, making it dry. The hot air itself, so the air is entering here through this is a heat exchanger. So in the heat exchanger, there has to be a heat source. You can have even electrical heaters. Some of the tray dryers have electrical heaters. The purpose is we want to make hot air. Air should be hot. So this hot air will go and dry the product. In this case, as we went inside, we saw a boiler. There was a boiler, and there was also a thermic fluid heater. So boiler and thermic fluid heater in the same shop. So it was quite surprising. And as we asked the person in charge, he was telling that initially they were using a steam boiler. So the boiler is a small boiler, 250 kg per hour boiler, small boiler, diesel fired. So it used to generate steam, and steam was sent to the heaters. So they were using hot air, and they said it was consuming an enormous quantity of diesel. So somebody else said, this is a boiler. So some other manufacturer came and suggested, instead of boiler, you go for thermic fluid, it reduces diesel consumption. So then they put up a thermic fluid heater, again a small one, a small thermic fluid heater. And thermic fluid will go into the heater, it will circulate and come back. Again, diesel is used. So they said, okay, they were saving energy, so they discarded this boiler and they were using thermic fluid. But we know that from the basics, there is nothing like heat carrier, nothing like steam, especially for these kind of low temperature drying applications. This is only 90 degrees air temperature is required. So 90 degrees air temperature, steam is the best medium for drying. So what happens in the steam, as we boil water from 30 degree water, as you keep on heating the water, it becomes steam at the point B. And it doesn't become steam, it becomes water at 100 degrees. That is, it reaches the boiling point. If you further add heat, the phase changes from water to steam. At point C, it becomes fully steam, saturated steam. Now this heat, what you have added here, this is called the sensible heat. And this is called the latent heat. So this is what we are going to use in the dryer. So in the dryer, as we see here, the steam will go inside this dryer. The latent heat will condense as the air goes on the other side. So a lot of heat immediately is transferred to the air. Quick heating will take place and this hot air can be used. Then why this thermic fluid, which is operated between 200 degrees, for 90 degree air they are operating at 200 degrees, and why this should be used as an economical means? So that means, does that mean thermic fluid is more economical than boiler? What are the problems? So it was going against the basics, and then okay, we started the discussions and went around the whole system. Then we asked for the steam trap. So normally what will happen, the boiler steam will come, it will go into the heater or any equipment, heat exchanger. Then at the outlet, you will have a device called steam trap. So what is the purpose of steam trap? Steam trap will ensure that steam condenses and only the condensate comes out. That means the latent heat should be transferred to the air. In this case, surprisingly, there was no steam trap provided. So he was telling the boiler used to be on and steam used to go inside the heater and so much of steam used to go into the atmosphere. Then when the steam does not condense, how the air will get heated? So they kept on sending steam and the air temperature never used to reach 90 degrees. So they had a lot of problems. Then ultimately they condemned this and they went in for the thermic fluid heater. Appears to be successful, of course. But what they missed out was the steam trap, especially in SME type of industries, where the process knowledge may be great, so they are good at this production. But the simple thing, maybe costing 2,000, 3,000 rupees, because of this, they have gone in for a thermic fluid heater using thermic fluid. And later on, what we did was we provided a steam trap in the line. We operated the boiler and we noted the diesel consumption with this, diesel consumption with this. So the boiler was consuming less diesel to the tune of 20%. So 20% reduction in diesel consumption was there just by providing the steam trap. And this alone saved them 1.1 lakh rupees per annum. So the thing is, whatever we acquire in terms of knowledge, we need to look into the practical aspect. We go to the field, at the back of the mind. Some of these techniques, what we are discussing, it should be at the back of the mind, and you apply them. So a lot of saving potential is possible. So many times we find that energy audits are at a surface level. It may be a 500 megawatt power plant, then the major energy saving measure is you change the existing lamps to LED lamps, you put a turbo vent. So these are not the kind of recommendations that we look from professional energy auditors, and not only we, but the client themselves. They're looking for something, not a miracle, but some well-evaluated audits need not always result in energy savings. Even after auditing, you tell them that, okay, we have done the audit, everything is fine, there is no scope for saving. That is also a good audit. But just for the sake of showing some energy saving measures or filling up the report, we provide unnecessary data, unnecessary measurements, so it doesn't help. So energy auditors should focus on the process, You have a process-based approach. Look into the process, observe the process, and then you see what is the energy interaction that is happening. So, for example, here, sometimes this happens. So, in a big industry, maybe about 2000 kVA is the contract demand. So, one of the recommendations, the electrical parameters, including voltage, current, power factor, were measured for few of the motors. The details are under. The motor were observed to be appropriately loaded. What is that we get out of this? And you see there's so many data there. So the equipment details are there. The rated kilowatts, voltage, amps, kilowatt, tron, power factor, load percentage. Right. This is all fine. Some effort has gone into this. Measurements, making this stable, and the suggestion is appropriately loaded. Good. What is the takeaway? Is there anything that the industry gains? So when you say appropriate loaded, okay, it gives some information, but it's an instantaneous reading. At the point of time when you are taking the reading, it was appropriate loaded. How do you analyze the variations in the load with respect to time? So we don't know. So these kind of things, measurement without purpose, we tend to lose focus. And this is another very strange case where, the compressor is a motor pulley belt slippage. So what has been done is, the various motors, we have measured, the pulley sizes have been measured, and this formula is also mentioned, pulley diameters. So rated RPM is there. What is the driven RPM, the drive RPM? What is the slippage has been calculated. So motor slip or the equipment slip has been calculated. So the belt slippage. So one machine it is 1.7%, one machine is 11%, 2.6%. So what is that? Belt slip shows considerable variation from 1.7 to 7. The slippage needs to be negligible for a well-designed system, but typically acceptable belt slippage is less than 1%. The slippage leads to proportional loss of motor energy and need to be monitored and controlled at regular intervals. It is suggested to check the belt slippage at periodical interval and take remedial measures, including replacement of on-outputs, adjusting the distances, servicing, tightening of the system, etc. The system may be redesigned in case of persistent slippage. So what do we get out of this? Okay, there's a belt slip, so what? So slippage itself is not going to consume energy. If the belt is slipping, then the lesser energy will be consumed, which is good. So these kind of measures actually takes the focus out of the audit. So our audit has to be highly concentrated, and it should be focused. And these kind of measures, maybe from a different angle, it may be useful, but not from the energy audit point of view. So also this, this indiscriminate use of the power analyzer. Keep on taking all kinds of measurements possible. Somebody says my meter can measure 150 parameters. So what? What is that you're going to do with 150 parameters? All that we need is kW. We are not concerned with any other parameter. In some cases, of course, a power factor when you are, checking with the grid meter. But otherwise, simple thing what we want is kW. kW before, kW after. Some change you have made. What is the difference? So I'm also surprised that many of even the clients ask for calibration of meters. It's really surprising. See, we're not here to design things. We are here to save energy and estimate. Probably this is the extent of savings that is possible. We are not here to accurately, pinpointedly say that this is the energy that will be drawn. And that doesn't need a calibrated meter to check and verify. And I'm even more surprised there are certified monitoring and verification professionals available for checking the energy savings. So what has been the impact of such monitoring? Are they going to do something extra than what the energy auditor is doing, or the plant people are doing, or any engineer is doing? Ultimately, we want to know what is the extent of energy savings, and this itself is a projection we are making. Suppose you put a VFD for the pump, and we say this is going to be the projected savings, and this is going to be the payback. It can vary. So many things can keep varying, depending on the load, depending on the raw materials, depending on the weather conditions. So much variations are going to take place. So we are not really bothered about accuracy of KW reading. Instead of 7 kilowatt, if it is showing 7.2 kilowatt, doesn't matter. It should not show 1 kilowatt, of course. So, the talk of calibrations and then certified verifier to verify the energy savings, it doesn't make any sense. The client should be happy and you should accept that, okay, whatever projections you're making is acceptable to us. That is sufficient. We don't need to complicate the audit. Many times, the client himself asks, do you have these equipment? Wet bulb temperature, dry bulb temperature, infrared temperature gun, ultrasonic flow meter. The engineering industry, there is no water at all, no pump at all. He says ultrasonic flow meter you should have. What is the use? So we need to bring in some kind of system where we simplify many of the things which are unwanted. Focus only on the energy saving aspects, energy usage, energy savings. Ultimately, there has to be a reduction in the energy bill. Good for the client and good for the energy auditor. So he can focus more on the various energy saving opportunities, how to arrive at energy saving opportunities, what are the latest trends. So this is where an energy auditor needs to focus. You should not be focusing on maintaining the equipment, instruments, buying lakhs and lakhs worth of instruments, then calibrating again with lakhs and lakhs of rupees. So finally, what for? These are the questions that we need to ask ourselves. Okay, so a good purposeful energy audit should focus on the process, identify the interaction of energy with the process, and identify measures which will be unique. So as we said, we are not looking at standard measures, reducing the pressure of compressor, putting VFD for the compressor, making heat recovery from the compressor, but how do you integrate with the process? Heat recovery from the compressor is good. It's a standard solution that is available. But where is the hot water required in the process? Where we can possibly use this hot water? These are the things that energy auditor should look for and see how it can be integrated with the process conditions. Okay, so this is what I just wanted to share. Now we can take some questions. Sharath?
Yes, sir. Thank you for the presentation, sir. There are some few questions, sir.
Yeah.
This is question from Anish. As per BE guidelines, what are all the power quality parameters mandatorily to be shown in the energy audit report? Is it only THD, dips and swells events?
No. See, that is the problem. This is what we're discussing now. The BE mandatory and all that doesn't talk about what parameters need to be measured. It only talks about specific energy consumption. So in a typical PAT audit, we are only looking at MTOE or kWh per ton of specific energy consumption. So BE never mentions about harmonics and THD and all that. In fact, that is another thing that was going on, of course, quite some years back, where harmonics was claimed to be a subject which is not well known to many other people. So there were people in the market who said we'll reduce the harmonics, and reducing harmonics will save 20% of energy, 30% of energy. So many things went around. Similarly, additives, that's another big market. So they say you put this additive in this fuel, immediately 10% fuel will be saved. So these are the things which are not required. So harmonics is a separate subject by itself, which is best left to the electrical engineers. Energy saving is entirely different. It has nothing to do with harmonics. So harmonics is a result of, okay, you have a VFD, then okay, harmonics occurs, that's okay. That will be taken care of by the specification issued to the vendor, where he will say the harmonic limit has to be within this. And even beyond that, some steel plants, they suffer from too much of harmonics with all DC motors and all that. So there are separate specialists to look after the harmonic. Energy auditors, we should stick only to energy audits, energy conservation, measure only the power. kW is what is required, nothing else, no other parameter. Many of the power analysis, we have so many parameters there, we are not going to use them at all. So we are only looking at kW. Yeah, next question.
Sure, sir. It's a question from Unikrishna Prasad, sir. VFD shall be of high standards as well as it affect badly with the harmonics. Will it create a problem?
See, there is always a problem. Nothing like, you won't find anybody, have you seen any person saying, I don't have any problems at all? Even Buddha had a problem. Jesus had problems. Gandhi had problems. So problems are there everywhere. You can't have a problem-free life. Similarly, equipment. You want energy saving, you put a VFD, there is another problem, harmonic problem. But again, then there are systems and solutions to mitigate the harmonic problems. So these are all things that we have to live with. There is nothing like total elimination of problems. The problems get shifted from one place to another place, from one form to another form. So ultimately, that is why we are there. If there is no problem, everything is a magic. You put a VFD and forget. Energy saving 50% you got, then you won't have any job. You won't be required in the industry. So there needs to be problems. Only then we can all survive. If there are no problems in any industry, then there'll be a huge unemployment problem. So problems should be there. It is there, and we are there to solve it. So that is happening simultaneously. Yeah.
So the next question is from Mr. Suresh Babu. Typically, newspaper industry have a specific energy consumption of 20 watt-hour per copy. Is there an external benchmark for that?
See, the benchmarking, of course, if it is a standard product, then there is a benchmark available. But otherwise, benchmarking is again, is something well said on paper. So when you're comparing two different units, within the same unit, if you benchmark, last month what was the energy consumption, this month what is the energy consumption, what is the best. So even in that, there are a lot of variations that take place. So benchmarking can be quite tricky to arrive at the, what is a norm against which you have to compare with. So that's quite tricky, and the specific thing about printing and 20 watt hours can vary with so many parameters. What is the intensity of printing that you have to do on a page? Suppose the Word document completely filled with all kinds of fonts and material. The entire page is going to be printed, then it's going to have a different consumption. Suppose if it's only an invoice, maybe about 6 or 7 lines only are going to be there. Then the energy consumption may change. So there are a lot of variations that take place. So benchmark is something which is again not very reliable. Even the cement plants. So cement plants, they have benchmark values, but still with so much of standardization in the cement plants, still we find that there are a lot of variation. Within the plant itself, there are so many variations that take place.
Okay, so one more question.
Yeah, next. Yeah.
Whether ST motors and LT motors makes any efficiency improvement if motors are higher rated?
HT motors beyond a particular rating will be beneficial. One, because when you are using high voltage, the size of the motor will be smaller, and of course the efficiency will be slightly more compared to an LT motor. LT motor, the current, of course, is basically, again, fundamentally, if you see, if you're using high voltage, the current will be less and the I squared R loss in the stator rotor will be less. So the efficiency will be slightly higher and size will be smaller. So vice versa for the LT motor.
Yes, sir.
Yeah.
Thank you. And the next question is, in the electrical system, cable loss are also considerable. It also has some potential for savings. This also requires serious consideration. Isn't it correct?
Actually, it is not correct because we have seen in earliest of slides, distribution law, when you're talking about, again, what distribution law? Is it for the entire grid? For the distribution company, it may be significant because they have a huge network of lines in a distribution system. So the distribution loss, technically, the loss can be somewhere between 10 to 15% maximum. In countries like Norway, Sweden, and all, it's only 3 to 4% in the distribution network. That means we're talking about a city distribution network or a total discom network. But within an industry, if you see, it is hardly anything. We may have 1 kilometer of cable. In that 1 kilometer of cable, what is the current that is going? What is the size of the conductor you're using? All this, if you take into account, it may be less than 0.2%. So 0.2% is not very significant. And there is nothing that you can do about it, and there is nothing that we need to do about it also. We can just ignore. Some losses will be there. These are all very minor losses. So no point in focusing more on these kind of distribution loss reduction within an industry. Yeah, next question.
So next question is from Mr. Abhay Nagle. His question is, Hi, Mr. Nagesh. We had very briefly discussed this day before yesterday. Sorry to report. Will it not be an interesting case to discuss air cooler that serves as a preservative condenser upstream to main condenser in a power plant?
Yeah, that's what I think that question was also answered. If you have an air-cooled condenser, your question is, there is a water-cooled condenser. We want to put one more air-cooled condenser before the water-cooled condenser. Probably want to save on water or whatever it is. So, an air-cooled condenser before the water-cooled condenser, what is going to be the impact? So it can reduce the water temperature by a few degrees, no doubt. But then you're going to spend some power on the fans. So air-cooled condenser fans, they also, what you need maybe about 10 to 12 fans of 5.5 kilowatt perhaps. So is that going to be economical? So reducing a few degree temperature using these fans. So how much it is going to impact on the water consumption? How much water are you going to save? So rather than that, the focus should be on how to improve the vacuum by cooling it as close to the wet bulb temperature as possible, the cooling water, so that your vacuum improves and the power generation improves. So for maybe for interest sake, you can take up calculation, work out what will be the fan power consumption vis-a-vis a few degree reduction water temperature as a pre-condenser to the water-cooled condenser. Then you know. So prima facie, it may not be economically viable. But still, you can work it out and see. If there is data, we can work it out.
Disconnected solar PVs are being installed in some industries to reduce grid energy consumption. Problem is observed with regard to meter low power factor in such cases. Also, DG operation is getting inefficient due to lower PF when solar PV is connected to DG supply.
Yeah, this requires some detailed answer, but then we'll reply to you in this as we consolidate these questions.
Okay, sir. The next question is, can you suggest some publications or books related to energy conservation in industries.
What we can suggest is that be guidebooks which are freely downloadable from the internet. So they're a good source of information. So if you're beginning to do energy audits, then that is sufficient, I think. So it's quite a good source of information. It's freely available.
Okay, so I think it's time, so we can conclude it. I hope the presentation from Nagesh was very interesting and informative to the speakers. And I think we have missed some questions also. That we will be consolidating it and preparing an FAQ booklet, and we'll be forwarding it to all the participants. So on behalf of Energy Management Center and all the staff of EMC, I once again thank Mr. Nagesh sir for his valuable session. And I also thank you for all the participants who attended the webinar. And this room will be open for another 10 minutes. So if participants have any doubt regarding the presentation, you may please post it in the chat box. And we'll be collecting all the queries, and we will be preparing a booklet and we'll be forwarding to everyone. And thank you once again. And all are requested to kindly save the feedback form also.
Thank you. Thank you. Thank you.
Thank you, sir. Thank you, Nagesh. Thank you for
Thank you very much. Thank you very much to all the participants. Thank you very much.